So experimental physicists have to be what I call approximate theorists if they really want to do something. Now, a theorist would not make the measurement. He or she would sit down and calculate a process and try to get the exact number to be as accurate as possible. And that's the difference. And therefore, so an experimentalist may want to get an approximate number, but then he wants to get an exact measurement. And then ultimately that exact measurement is compared with the exact calculation. And that's how you make progress. But sometimes the calculations are too complicated and experiment has to lead. And that's what happened.
Thank you very much.
First of all, good afternoon. This is a question I always ask to my physics teachers, and they haven't answered to me. How do you separate a particle, in this case an electron, from its atom? How do you use it in a hadron collider? How do you do that?
Yeah, she always asks her physics teacher and they never answer. How do they separate the particle?
How do you separate an electron?
The electrons from the atom?
What?
Oh, okay. That's very simple. You can bombard them with gamma rays. You can bombard them with electrons. Any collision which comes in the vicinity of an atom will collide. For example, if you use a high-energy gamma ray, it will interact with the electron and give it enough energy to be pushed out of its orbit, and you actually will ionize that atom. And you can do that with electrons. You can do that with all kinds of things. All you can do is find some method of supplying enough energy to basically decouple an electron from its orbit, and that's all. It's not a complicated thing.
Well, thanks.
Two more questions. You, sir, and then you.
Hi. I have a kind of personal question because, as I see, you are the one of few people who can answer this. And in centuries before, when a brilliant mind had an idea and say, for example, I don't see the Earth like a plate, but like a balloon. And the genius, as you say, told, that's wrong, you're wrong, that's against God. And you need to be punished or excited. And after time, when they discovered he was right, they was like, oops, we made a mistake, we forgive you and thanks anyway. But as the time goes by, now you are here, you present your work, it's accepted by all over the world, and we are here celebrating, and you are alive, and you can say to the genius, you are wrong. And I really want to know what does it feel like to be alive and see all your life work complete, succeed. I want to know what does it feel like.
Well, let me say the following: it's a wonderful feeling. You know, getting the Nobel Prize was absolutely a joy, and you know, it was like unbelievable. But I must tell you, the greatest pleasure wasn't actually doing the work. It was so exciting during that period of time that we just couldn't contain our excitement. As everything developed, it all fell into place, and it was so exciting, and it was as though we were so lucky and so privileged to to be in that situation where we had that accelerator, we had decided to do that experiment, and nature was showing us something new. I mean, it's just so absolutely exciting. I keep on repeating because there's almost no other word that I can find to describe it. But it's wonderful. Fortunately, society has developed into a point where there aren't these repressive political points of view which say that you're not allowed to measure this or measure that, or if you say something that is outside the acceptable range, you're either put in prison or some other terrible thing happens to you. Fortunately, we're not in that case, and so we have made a lot of progress as a civilization. I mean, the last time, we had such a problem was in World War II, when, for example, when the Nazis came in. Einstein's work was called Jewish physics, and if you were a good Nazi, you couldn't believe it. You have to discard it. And then there was also in the Soviet Union, Stalin basically was pushing the work of Lysenko, which said that inheritance was not very important. Actually, it was all basically the environment which created the characteristics of plants and so forth. And so, fortunately, we are now in a much better type of civilization, thank goodness. But I thank you for the question, because it brings back wonderful memories.
I have a question about curiosity. You said science is curiosity, and I believe you're a very, very curious man, because you chose your career based on a doubt instead of a certainty. You said you had a question that you wanted to solve, so you left arts on the side and you decided to go through physics, which isn't something everyone would do. So when you were in high school, you read a book with lots of equations, and you didn't back down. You went up to it. You took the challenge. I think that's why you're very, very curious. Sadly, nowadays, generations aren't as curious as they used to be, or I think our students, they don't make enough questions about the things we teach them. So how is it possible to feed curiosity? Because if it's the root of science or the main ingredient, how is it possible to motivate them, to make them more curious about things, about the world, I think it's something we need in every domain, to be curious, but how do you feed it? How do you maintain it? How do you keep it alive?
Okay, that's a very good question. How do we create curiosity and maintain curiosity among young people? Is that fundamentally what the question is?
Yeah, and through life, but young people.
Well, if you start young people at an early age and you excite their curiosity, and the school system doesn't squelch it, then that person will end up being curious for the rest of his or her life. Part of the problem is that it's always said, and it's true, that children are original scientists. Because what does a scientist want to do? The scientist wants to know how the world works. When a child comes into connection with the environment and the world around him or her, that's exactly what the child is trying to understand. And the child wants to know why this, why that, and so at some stage in school, people are said, well, that's not important. You'll learn that later. Sometimes it comes from teachers not really knowing the answer, or teachers having a different point of view about how one should teach. I mean, for example, we have all these devices at home. We have cell phones, we have tablets, we have computers. And has anybody really sat, how many kids have sat down and said, gee, how does this work? I have this phone, I can talk to somebody thousands of miles away. There's not even a wire connected to it. How does it work? Now, what happens if a student, let's say in the second or third grade, goes and asks the teacher about how it works? Well, unless there's a and attempt to really answer it in a way in which a child could comprehend and excite the child's curiosity, that child may be squelched. It may stop asking questions. And we can't do that. So we have to, in the school system, we have to have what I call inquiry-based education as well as other types. What I mean by inquiry-based education, we have to ask, try to get students to think about how things work around them. And they can understand it in terms of very simplified concepts. I'll tell you a little example I had. It was really interesting, then I'll stop. Once I was visiting a laboratory, and they said I was going to go visit a school. They wanted me to come and visit a school, so they took me to the 5th grade. And then I went in, I said hello to the students there. I thought it'd be fine. Now you have this class for 25 minutes. She had never told me I had a class for 25 minutes. What am I going to do with a class of 5th graders or so in 25 minutes? I hadn't prepared anything. So I was standing there, I looked up at the ceiling, and I saw this light. And sort of a light turned on over my head. And I said, oh, we're going to have a little question today. How does that light work? Why does it give us light? And I want you to think about it for 5 minutes. And then I want each of you to tell the others what your theory is. So that way I was able to use up 25 minutes quite rapidly. But the point is, these kids were so excited about thinking about it and trying to develop an idea of how it worked that they really were excited. And I held their interest. And then after we went through all the various possibilities, I gave them a little lecture on how the light bulb worked. And they were very excited. And to me, it showed that even little questions like that can have an enormous impact on kids. We have to do more of that. And we have to get away from having kids memorize formulas. That's the way to kill science. We should have to memorize concepts and ideas. Later they can memorize formulas once they're hooked. But don't have them memorize formulas too early. So that's my long answer to a short question.
One more question. Our feature student here. Go ahead.
Well, good afternoon. And my question is, when you discovered the quarks, why do you put the name quark?
Why do you call it quark?
Oh, that's a good question.
So what's the meaning?
Okay, let me. That's a very good question. And there were two people who proposed the quark model. One was Murray Gell-Mann, who called them quarks, and there was George Zweig, who called them aces. And it's quite interesting that the quark name survived, and I have a theory about that. And the reason that it survived is because it was a nonsense name for a nonsense theory. and quark, and the word quark actually came from, and this is Murray Gell-Mann, he took it from a novel written by James Joyce. It's called Finnegan's Wake. And there's a passage in there where there's a drunk person talking, and he says, 3 quarks for Mr. Mark. What he meant to say is 3 quarts for Mr. Mark, but because he was inebriated, he said 3 quarks for